All right, so in this question, we're going to take a look at just some introductory carbohydrate topics. And here we're looking at understanding the descriptive vocabulary of monosaccharides. We need to draw the Fisher projection of a D-aldotetrose. So first of all, what does that actually mean? So D-aldotetrose. So the name tells us a little something about the actual sugar, right? And these are monosaccharides. These are individual sugar units, the smallest of the sugars. So the tetra part here tells us that this sugar is made up of 4 carbons. And then the O's just tells us that it's a sugar. The aldo part tells us that there's an aldehyde group present. Remember, aldehyde has a C double bond O connected to an H, and then that 4th bond is to the rest of the molecule. Aldehydes are found at the ends, usually the top end of our Fisher projection. And then the D tells us that the OH on the last chiral carbon is on the right of the structure. Right, and that's relative. Usually that chiral carbon is furthest to the bottom, usually the second to last carbon in our Fisher projection. So if I were to draw this, and again, I'd recommend drawing these out on a sheet of paper and then doing it in ALEKS. So I have 4 carbons. So I have 1, 2, 3, and then 4 here at the bottom. It usually ends in a CH2OH. My aldehyde for an aldotetrose would be at the top. So I have my C double bond O connected to an H. All right, so this makes it an aldo. And I have 1, 2, 3, 4 carbons. And then the OH on the last chiral carbon, which in this case is carbon number 3, is going to be to the right. And then I'm just going to put in my H here on the other side. It doesn't matter on carbon 2 where you put your OH. In this case, I can put it on the right side. On carbon 2, I could also put it on the left. That's not really specified in the question. So when I go into my molecule builder in ALEKS, I'm going to select here. You see now there's a skeleton I can choose. I have 1, I move it around. I add it to a second one right about there. So I have 1, 2, 3, 4 carbons, and I can go ahead and now edit my structure to look kind of like the one I drew here. So I need a C double bond O here at the top. Let's put that C in first. So you have a carbon. I need a double bond. So 1 bond and another one. That's going to be to an oxygen here at the top. And then my 4th bond there to the carbon is going to be to an H. Put that H in. Then here at the bottom, I have a CH2OH. And it's a D sugar, so that OH there on the last chiral carbon is going to be to the right side. Put the H on the other side, and then the remaining carbon, I can put the OH on either side. It doesn't matter because that's not specified in the question. All right, so I have my structure drawn. That looks just like this. If I check it, hopefully, fingers crossed, there we go. That's correct. All right, so in this one, we're looking at drawing the Fisher projection of the enantiomer of a monosaccharide. All right, and enantiomers are mirror images. Specifically, they're non-superimposable mirror images of each other. So for example, if I'm given these 2 options here, it's asking me, are these 2 enantiomers? And the first thing is to realize is that enantiomers are nothing more than a type of isomer, which means that they have to have the same molecular formula, but in this case, they're just mirror images of each other. So, and you look at these 2 options, you can probably see in the first one here, we have 1, 2, 3, 4, 5, 6 carbons. And the one on the right, we have 1, 2, 3, 4, 5, right? So these are obviously different things. One has 6 carbons, one has 5 carbons. So the formulas are going to be different. So what we need to do is you can edit either one of these 2 to make it the enantiomer of the other one. All right. So in this case, they're not enantiomers, so we need to adjust it, and we'll adjust the one here on the left side. So I need this one here to have 1, 2, 3, 4, 5 carbons. Right now it's got 1, 2, 3, 4, 5, 6. So I'm going to erase the carbon there at the top. All right, and that now, just like as the top here, we have an aldehyde group. I'm going to put an H in there at the top. Now I need, you can imagine that there's a mirror between these two. So whatever is on the closest to the mirror on one side needs to be closest to the mirror on the other side. All right, so if I have an OH to the right here, there should be an OH to the left because that's reflected. So here should be an OH. Let's put that OH in, which means the H now is going to be on the other side. Similarly here, OH to the right should be an OH to the left. And we'll change the other side to an H. And here now we have an H to the right. This should be an H to the left. We'll put the OH to the left side on this carbon. It should be to the right side on this one here. All right, so if we check there, hopefully you can see that those are mirror images of each other. All right, so this, it's telling us now that this is not drawn according to the usual rules. So probably what ALEKS is saying is up here, you'll notice that in our structure that wasn't changed, the OH, I'm sorry, the aldehyde were drawn in their normal trigonal planar shape, and that's the shape that we want to keep here on the left side as well. All right, so just to clarify what the issue was, we saw this in some of the earlier structures. So ALEKS is pretty picky about where you draw your bonds and what they are actually connected to. So down here, actually, when we put the OHs in into those, it's very important that you put them in the right order. All right, so for example, down here at the bottom, this one over here, I had the H here on the right, and then I had an OH like this, right? Which indicates that the bond here is actually to the H. It shouldn't be like that. You actually need to type in H, you need to type in HO so that this bond is connected to the oxygen and then the H. All right, so if I wanted to see here, if I put that in over here, let's try another one actually. And I'm just going to change this. Let's see here. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. All right. So again, we need to change. You can change the one on the right. We're going to erase the top here. We're going to replace that bond with an H to make it an aldehyde. Whoops. And I put my H in, and now I need the OHs here on the left side, right? So if I just type in, if I use the pre-selected OH, you'll notice here that it's OH when it actually should be HO. So I'm going to have to type that in like so and change all of them. You type in uppercase HO to show that the bond is actually to the oxygen and not the hydrogen of the hydroxyl group. We'll change the other side now to H's as well. And that then would get us, if we check that, those look like mirror images, and that should be correct. So just be careful when you draw your structures here. The OH, the hydroxyl group, the bond has to be to the O of the hydroxyl group. All right, so in this one, we're going to show how we can convert the Fisher projection, which is the chain, to the Haworth structure, which is the ring structure. Remember now, the ring structures are usually the most stable form of our sugars because having that ring makes it a little bit more unreactive than having an open chain, right? And remember, stability is sort of an underlying theme through our chemistry. All right, so we have here now, we're given an aldose. So this is a 1, 2, 3, 4, 5. So this is an aldo pentose that we have. 1, 2, 3, 4, and then our CH2OH here at the bottom. We have our H, And then H's here on the left, we fill in our OHs. So the way that we want to draw these, right? If you have a in this case, 5 carbon chain, right? We're going to end up making a ring structure that is going to be a 5-sided ring structure. And the way that it's going to happen now is that the carbon number 1 here that we have, this carbon, is going to react with the second to last carbon from the bottom, right? Which in this case would be carbon number 4. So when they fold up around, you actually end up making now a 5-sided ring. All right, so we have 1, 2, 3, 4, and then at the top of the ring, or one corner of the ring, instead of having a carbon, we actually have an oxygen that makes up a point of the ring. All right, so if we were to number our carbon, so this is carbon 1. Let's number them in the different colors. So this is carbon 1, 2, 3, 4, and 5. So in our ring structure now, we end up forming a 5-sided ring with an oxygen being at one point of it. This is going to be our carbon 1. This is 2, 3, 4, and then we actually have now carbon 5 with the CH2OH that comes off of the ring. So we have our CH2OH up here, right? And that's your carbon number 5. And that's very similar to what we saw with a 6-sided ring, as you will see in the videos with glucose. So on carbon 1, which is this one here, the original one that had the aldehyde in it, we're going to have a couple things attached to it. Also carbon 2, carbon 3, and then carbon 4 is also going to have, in addition to that CH2OH, we also have that H. On all the other carbons, 1, 2, and 3, we're going to have H's and OH's attached to them. All right, so let's do carbons 2 and 3 for right now. So in carbon 2, the OH is on the left side of the Fisher projection, which means in the Haworth is going to be pointing up. So we'll have an OH here. And on carbon 3, we have an OH to the left. It's going to be pointing up as well. We'll have an OH there. We fill in the H's on the bottom. And then on carbon 1, because now we don't have an OH here, we actually make a new OH. And we're not told whether it is the alpha or the beta form of this, so we can put it wherever we want, with an OH there and H at the bottom, right? So I'll circle those OHs where they corresponded, where they pointed to the left in the Fisher projection, they go up in the Haworth structure. So when we draw this in our ALEKS tool, we can add the molecule skeleton. There's our 5-sided or furanose ring. Put that right there, and then we can just fill in our bonds, right? So we need let's start on carbon 1. We have an OH, and we have an H. We'll just add those in for right now. And the good thing about ALEKS here is it kind of tells you where to put those, so it looks kind of neat. Okay, and then we'll just fill in the remaining things. So we need a CH2OH here. We need an H there at the bottom. On carbon number 3, we had an OH here at the top, and double check that the bond is to the oxygen. OH in the bottom, or H on the bottom. On this one, we have an OH at the top, H at the bottom. And then we said that it didn't matter where we put it on carbon 1. In this case, put the OH in the top, H on the bottom. And that should be our 5-sided ring structure, which is the Haworth projection of the Haworth structure. All right, so in this one, we are actually given the cyclic or the Haworth structure. And what we need to do is we need to identify different parts of it. All right, so we'll draw it here on the right side first. So we have a 5-sided ring. Carbon 1, we have an H and an OH. Carbon 2, OH on top, H on the bottom, carbon 3, OH on the bottom, H on the top, and then our CH2, OH, that's our carbon number 5, and H on the bottom. All right, first thing it says, first make sure this is the alpha anomer. So how do we decide whether it's the alpha or the beta? Well, we look at this carbon right here. The OH is pointing down. Okay, OH is down, which means that it is the alpha. We don't need to change that. If the OH was pointing up, then it would be the beta form, and we'd need to change it. Then replace the hydroxyl group on carbon number 5. So let's number the carbons. This is carbon 1. This is carbon 1. Let's see if we get that. This is carbon 1. This is 2, 3, 4, and 5, right? So what we need to do is to replace the hydroxyl group here with a Cl. So in our structure, let's go in. We want to erase that OH right here. We want a CH2 Cl. All right, so let's see if we can type that in. All right, and then we can check. I don't think there's any other changes we need to make. All right, and there we go. So you want to identify alpha versus beta, and then if they ask you to make changes, you want to identify the correct number of carbons in your structure. All right, so in this one, it's asking you to take a look at polysaccharides, and in this case, it's asking you to draw a tiny section of the molecule amylopectin, right? So we need to remember some of the characteristics of amylopectin, which is one of the components of starch. So amylopectin is made up of glucose units, okay? And the glucoses are connected by, so it's going to be made up of a chain of glucoses. And then there are also branches. Okay, and the branches are alpha-1, 6 branches. The chain of glucoses are connected by alpha-1, 4 glycosidic bonds. So it's asking you to use these templates or these starter molecules. Obviously, that's your glucose. These are not anything close to glucoses. So let's erase those. So we can select this here. We want to erase it. We want to erase that one. And then it says we need to use at least 4 monomers to show how these are connected. And then we're going to have a branch here of alpha-1, 6. All right, so we're going to take this, we're going to copy it. So we're going to copy, and we're going to put it be right there. We'll copy again. And another one right there. Oops, this. Let's erase that, actually. Okay, let's do that again. We're going to copy, paste, and then we're going to copy and paste it right here. So we'll have 3 of them connected. We need to show a branch. So we'll put the branch here at the top, and then we'll go ahead and connect them here in a second. All right, so we have our 3 glucoses in a chain. We need to connect them with the alpha-1, 4, right? So remember, this is carbon 1, 2, 3, 4, 5, 6. So here it's 1, 2, 3, 4, 5, 6. So this is carbon 1 from the first, carbon 4 from the second. We need to connect those with a glycosidic bond, which is simply connecting them with an O, an oxygen between them. So we need to erase this bond here, that OH. We're going to erase that bond too, erase this one, erase that one. We're going to make a new bond going this way, and make a new bond going that way. Whoops. Well, let's not make that bond yet. We'll have our O at the end. And then we're connected to that carbon. That is my alpha-1, 4 glycosidic bond. I'm going to do the same thing to connect the remaining 2 sugars here with the same type of bond, connected to an O, and then a bond to the next one. Okay, so that's my chain. I have 3 glucoses connected to each other. I also need to make a branch. So in this middle one here, and to the one on the top, this is a glucose. This is carbon 1. I need to connect carbon 1 to carbon number 6 of the chain underneath. All right, so I'm going to erase this bond and that one. I'm going to erase this bond here, and I'm going to replace this with an O. I don't want to erase that. I'm going to put an O right here, and then I'm going to connect that now to that carbon like so. So this is my alpha 1, 6 branch, and then my alpha 1, 4 chain of glucoses. All right, let's check and see whether it takes that. It's taken a while. It says it's wrong. All right, so let's see what's the issue with this. All right, so it says blah, 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 blah. Explanation. Okay, so it gives us some additional information. All right, so we have here, it's giving us our structure, which is kind of what we have drawn. Let's see. Oh, I erased everything. All right, so what ALEKS is looking for here, and again, it can be a little picky sometimes. We had the general layout of the structure drawn properly. However, you don't need to show your H's in your structure, and you don't need to explicitly show the carbons either, right? So, for example, there's a CH2 here that's understood to be present. There's H's here on each of these carbons that are not shown either. All right, so in this question is asking you, it's actually giving you a section of a polysaccharide, and you need to identify the glycosidic bonds in the molecules. All right, so the glycosidic bond, if you look here, we have a chain, we also have a branch, and this kind of looks like a 1,4, an alpha 1,4 glycosidic. So this would be what you would have in several things, but the fact that you have this alpha 1,6 branch means that it can be in either amylopectin or it can be in glycogen, right, which has the same type of bonding but way more branches. So let's back up here. We can highlight the glycosidic bond. So the 1,4 glycosidic bond is this one. The 1,4 glycosidic bond is that one. So these make up the chain, and then the 1,6 would be here connecting carbon 1 to carbon number 6. Let's see what else. So it says list the symbols for each type of glycosidic bond. Well, we already identified these. So let's see. We have alpha. Let's see. Let's erase that. We have an alpha 1,4. So 1 to 4, and then we also have alpha 1,6. So alpha 1 to 6. And again, we can find that in amylopectin and also glycogen. All right.